A landscape that millions of visitors have admired for generations has changed once again, raising fresh questions about one of the most closely monitored volcanic regions on Earth. Yellowstone National Park has experienced another significant hydrothermal event, and the evidence remains visible in the form of expanding fractures, newly formed vents, steaming pools, and altered terrain surrounding Biscuit Basin. A fresh explosion has reshaped part of the famous geothermal area, leaving many people asking an important series of questions. Is Yellowstone's volcanic system beginning to shift? Is magma moving closer to the surface? Or does this remarkable event reflect another chapter in the constantly changing hydrothermal activity that has defined the park for thousands of years? Fresh observations from scientists working inside Yellowstone National Park have confirmed that the landscape surrounding Black Diamond Pool has undergone additional changes following a powerful hydrothermal explosion that occurred during the summer of the previous year. Follow-up surveys have documented expanding cracks, the appearance of entirely new hydrothermal vents, the formation of a new boiling pool created through collapse, and periodic bursts of hot water reaching the surface near the Firehole River. Although these changes have attracted worldwide attention, Yellowstone Volcano Observatory continues to report that the overall volcanic alert level remains at normal, with its aviation color code staying green. That distinction is important because Yellowstone contains two interconnected but very different systems. One is the enormous volcanic system responsible for some of the largest eruptions known in Earth's history. The other consists of thousands of hydrothermal features powered by heat rising from deep underground. While the two systems share the same heat source, their behavior can differ dramatically. A hydrothermal explosion does not automatically signal an impending volcanic eruption, even though both ultimately depend upon heat generated within the Yellowstone volcanic complex. Recent mapping efforts have focused on Biscuit Basin, a geothermal area located only a short distance northwest of Old Faithful and connected to the larger Upper Geyser Basin. Visitors have long recognized Biscuit Basin for its colorful hot springs, geysers, silica formations, and constantly shifting geothermal activity. Yet even by Yellowstone standards, the recent changes stand out because they occurred over a relatively short period and continue evolving months after the original explosion. During detailed field examinations, scientists identified several new steam vents that did not exist before the hydrothermal blast. Steam now escapes from multiple openings scattered across the disturbed landscape, indicating that underground pathways carrying hot water and steam have been significantly reorganized. These newly established channels allow pressurized fluids to reach the surface through routes that were previously sealed by mineral deposits or solid rock. Equally significant is the expansion of cracking across the surrounding ground. Fractures extending outward from the explosion site have widened and lengthened as the hydrothermal system continues adjusting to the changes created during the blast. These cracks do not necessarily indicate tectonic fault movement or volcanic magma forcing its way upward. Instead, they often develop because hydrothermal explosions remove underground support, allowing surrounding rock layers to settle, shift, and fracture under their own weight, while heated water continues circulating through newly opened spaces. One of the most striking discoveries involves a newly formed boiling pool that did not exist before the explosion. This pool appears to have developed through collapse, meaning underground material supporting the surface gave way after the hydrothermal event altered the local plumbing system. Water now occupies the resulting depression, where temperatures remain high enough to sustain continuous boiling. Such features illustrate that Yellowstone's geothermal landscape remains exceptionally dynamic, with visible changes continuing long after the initial explosive event. Activity has also been documented near the Firehole River, where observers have recorded periodic spouting of hot water from recently established hydrothermal openings. These features lie downstream toward Midway Geyser Basin, another world-famous geothermal region containing Grand Prismatic Spring, while remaining relatively close to Old Faithful. Their appearance demonstrates that the hydrothermal changes are not confined exclusively to the immediate explosion crater, but instead involve portions of the broader underground plumbing network supplying heated water throughout Biscuit Basin. Understanding these developments requires distinguishing hydrothermal explosions from volcanic eruptions. Although both originate within geothermal environments, their mechanisms differ substantially. A hydrothermal explosion occurs when underground water becomes trapped under pressure, while being heated to temperatures exceeding its normal boiling point. Confined by overlying rock, the water remains liquid, despite containing enormous amounts of stored thermal energy. Once pressure is suddenly released through fracturing or structural failure, that superheated water flashes almost instantly into steam. Steam occupies far more volume than liquid water. As expansion occurs within fractions of a second, enormous pressure develops, violently fragmenting surrounding rock and ejecting debris into the air. Unlike volcanic eruptions, hydrothermal explosions generally involve little or no fresh magma reaching the surface. Instead, they are driven by rapid steam expansion resulting from changes in pressure inside Yellowstone's extensive hydrothermal plumbing system. That distinction explains why a dramatic explosion can occur without changing Yellowstone's official volcanic alert level. Scientists monitoring the park rely upon multiple independent indicators to determine whether volcanic unrest is increasing. These include earthquake activity, ground deformation measured through satellite and GPS observations, emissions of volcanic gases, changes in underground temperatures, and other geophysical measurements. At present, those monitoring systems continue indicating that Yellowstone's volcanic behavior remains within its expected background range, despite ongoing hydrothermal changes at Biscuit Basin. Nevertheless, the evolving conditions deserve careful attention because hydrothermal systems can remain unstable long after a major explosion. Underground channels carrying boiling water rarely settle into a new equilibrium immediately. Instead, they often continue shifting as mineral deposits dissolve. New fractures open. Existing pathways become blocked, and groundwater circulation gradually establishes different routes through the surrounding rock. Each adjustment has the potential to alter surface features, create new vents, expand existing fractures, or generate additional areas where steam and boiling water emerge. Much of Yellowstone's remarkable geothermal landscape owes its existence to this continual reorganization. Famous geysers periodically change eruption intervals. Hot springs shift color as water chemistry evolves. Mud pots expand or disappear. New fumaroles emerge while older ones become inactive. Entire pools have been known to drain unexpectedly after underground channels are redirected. These transformations have been documented throughout Yellowstone's recorded history, although major hydrothermal explosions capable of significantly reshaping the terrain occur much less frequently. The latest developments at Biscuit Basin therefore occupy an important position within Yellowstone's long geological record. They demonstrate that even without volcanic eruptions, the park remains one of Earth's most active hydrothermal environments, where immense underground heat continuously reshapes the landscape through processes that are both powerful and unpredictable. Steam and boiling water moving through Yellowstone's underground plumbing system follow pathways that are constantly changing. Those pathways resemble an intricate network of fractures, porous rocks, mineral-lined conduits, and cavities extending beneath much of the park's geothermal regions. Although many visitors see only the colorful pools and erupting geysers on the surface, the activity visible above ground represents only a small portion of an enormous hydrothermal circulation system hidden below. The recent changes at Biscuit Basin illustrate just how quickly that hidden system can reorganize itself after a major disturbance. Following the hydrothermal explosion, scientists documented that several existing surface features no longer behaved the same way they had before the event. Some vents that once released steam became quieter, while entirely new openings began venting hot gases and steam. This redistribution is consistent with changes in underground water pressure. Once a hydrothermal explosion fractures rock and opens new channels, heated water naturally begins seeking the paths offering the least resistance. As those new routes develop, older ones may receive less water, while previously inactive areas become energized. One of the most closely watched developments involves the expanding crack observed near Black Diamond Pool. Surface fractures within geothermal terrain are not unusual, but their continued growth indicates that the surrounding hydrothermal system remains in the process of adjusting. Cracks may widen gradually as underlying rock settles into newly created voids, while repeated cycles of heating and cooling place additional stress upon already fractured ground. Water entering those fractures can also dissolve minerals that previously cemented rocks together, allowing further expansion over time. Unlike tectonic earthquakes, which result from movement along major faults, many fractures inside geothermal basins form because heated water continuously alters the strength of surrounding rocks. Hot water rich in dissolved minerals slowly changes the chemical composition of volcanic deposits through hydrothermal alteration. Over many years, strong volcanic rocks can become transformed into softer clay-rich material that is more easily fractured or eroded. This weakening process contributes to the instability often observed around active thermal features. That instability explains why park officials frequently close sections of geothermal boardwalks following major hydrothermal events. Although the visible explosion may last only seconds, underground adjustments can continue for months or even years afterward. Areas appearing stable one day may experience additional settling or the sudden appearance of new steaming vents later. Restricting access allows scientists to monitor these evolving conditions while protecting visitors from hazards that are often invisible until they become active. Another notable change documented after the explosion is the presence of intermittent spouting near the Firehole River. These periodic bursts of hot water indicate that underground pressure occasionally builds within confined channels before escaping through recently opened vents. Unlike famous geysers, whose eruptions often follow relatively consistent cycles, newly formed hydrothermal vents may behave unpredictably as the underground plumbing continues establishing a new equilibrium. The Firehole River itself occupies a unique position within Yellowstone's geothermal landscape. Flowing through some of the park's most thermally active regions, portions of the river receive substantial inputs of heated groundwater from nearby hot springs, geysers, and thermal runoff. Water temperatures in certain sections remain unusually warm even during colder months because geothermal discharge continuously adds heat. Changes occurring near the river therefore receive careful attention, not only because they reveal evolving underground conditions, but also because they may influence localized water temperatures and chemical composition. Downstream from the recent activity lies Midway Geyser Basin, home to several of Yellowstone's best-known thermal features. Despite the proximity of these geothermal areas, each operates through its own interconnected yet distinct plumbing system. Pressure changes affecting one portion of the basin do not necessarily produce identical responses elsewhere. Nevertheless, scientists continue monitoring surrounding thermal regions for signs that underground adjustments are propagating beyond the immediate explosion site. Many people naturally wonder whether expanding cracks and new hydrothermal vents indicate that magma is rising toward the surface. Based upon current monitoring data, there is no evidence supporting that conclusion. Magma remains the ultimate source of heat driving Yellowstone's geothermal system. But the depth separating the magma reservoir from surface hydrothermal features is measured in several miles and several kilometers. The hydrothermal explosions occurring near the surface involve water, steam, and fractured rock, rather than fresh molten material reaching shallow depths. Modern imaging techniques have greatly improved understanding of Yellowstone's volcanic plumbing. Seismic studies reveal that the magma system beneath the park consists of multiple storage regions rather than a single enormous chamber filled entirely with molten rock. Much of this reservoir contains a mixture of solid crystals and partially molten material, instead of fully liquid magma. While sufficiently hot to supply geothermal energy, most of the rock remains only partially melted. Above these magma storage zones lies a much shallower region where groundwater circulates through fractured volcanic rocks. Heat gradually transfers upward from the deeper magma through conduction and the movement of hot fluids. As groundwater descends, it becomes heated before rising again toward the surface through cracks and permeable rock layers. This continuous circulation powers Yellowstone's thousands of hydrothermal features without requiring magma to approach the surface. One important consequence of this arrangement is that relatively small changes in underground permeability can dramatically alter surface activity. If mineral deposits seal an underground passage, pressure may accumulate elsewhere. If an explosion opens a new fracture, water immediately begins flowing along that easier route. Surface features respond accordingly, sometimes becoming more active, sometimes less active, and occasionally disappearing altogether while new ones emerge nearby. Yellowstone has experienced numerous examples of this behavior throughout recorded history. Several geysers have permanently changed eruption intervals following nearby seismic activity. Earthquakes have altered water levels within thermal pools hundreds of miles and hundreds of kilometers away from their epicenters. New hot springs have appeared unexpectedly after underground fractures redirected geothermal fluids. In some cases, formerly vigorous features gradually ceased operating as their water supply shifted into newly established channels. Hydrothermal explosions represent one of the most powerful expressions of these natural adjustments. Unlike volcanic eruptions driven by ascending magma, hydrothermal explosions result primarily from the enormous energy stored within superheated groundwater. Water trapped under pressure may remain liquid despite temperatures well above the normal boiling point. Once confinement fails, rapid conversion into steam releases tremendous energy capable of excavating craters, scattering rock fragments, uprooting vegetation, and permanently altering the surrounding landscape. Evidence of ancient hydrothermal explosions exists throughout Yellowstone National Park. Scientists have identified numerous explosion craters ranging from relatively small depressions to features spanning several hundred feet and more than 100 meters across. Some occurred thousands of years ago, while others are much younger in geological terms. Many have gradually filled with water, creating ponds that give little indication of the violent events responsible for their formation. The explosion at Biscuit Basin joins this long history of hydrothermal change. Although significant, it remains far smaller than some prehistoric hydrothermal explosions documented elsewhere in the park. Even so, its location within one of Yellowstone's most frequently visited geothermal areas has drawn exceptional public attention because visitors can readily observe the resulting landscape changes. One question continues appearing whenever Yellowstone experiences any unusual activity. Is the supervolcano waking up? Current scientific observations do not support that interpretation. Yellowstone's volcanic system remains active in the sense that it continues supplying heat to thousands of geothermal features, but active does not necessarily mean an eruption is approaching. Large volcanic systems often remain thermally active for hundreds of thousands or even millions of years between major eruptions. Yellowstone's monitoring network was specifically designed to detect changes that would suggest magma movement on a scale capable of increasing volcanic hazard. Hundreds of seismic stations, continuously operating GPS instruments, satellite observations measuring ground deformation, gas monitoring programs, and thermal surveys collectively provide one of the most comprehensive volcano monitoring systems anywhere in the world. At present, those observations continue indicating that the volcanic system as a whole remains stable even while localized hydrothermal conditions at Biscuit Basin continue evolving. That distinction is perhaps the most important conclusion emerging from the latest observations. Yellowstone is changing, but the changes currently being documented are occurring within its hydrothermal system, rather than signaling a broader shift in volcanic behavior. The expanding crack, newly formed boiling pool, additional steam vents, and intermittent hot water spouting all point toward an underground plumbing system still reorganizing after a powerful hydrothermal explosion. These developments deserve close scientific attention because hydrothermal environments are inherently dynamic and sometimes hazardous. At the same time, they remain consistent with the complex and continually evolving geothermal processes that have shaped Yellowstone's extraordinary landscape for thousands of years. Yellowstone's hydrothermal system will almost certainly continue evolving long after the visible signs of the recent explosion begin to fade. Fresh fractures may stabilize, while others slowly widen as heated water continues circulating through weakened volcanic rock. Mineral-rich water will gradually deposit silica around the newly formed boiling pool and steam vents, altering their shape over time. Some openings may eventually seal themselves as mineral deposits accumulate, while entirely new pathways may develop nearby. This constant cycle of construction, collapse, sealing, and reopening has shaped Yellowstone's geothermal landscape for thousands of years and remains one of the defining characteristics of the park. Even relatively small underground changes can produce noticeable differences at the surface. A slight increase in permeability along one fracture may redirect large volumes of hot water away from an established vent and toward another location. Pressure that once fed a quiet hot spring may instead begin escaping through a newly opened steam vent. These adjustments occur because Yellowstone's hydrothermal plumbing system is interconnected, with water continuously responding to the easiest available pathways beneath the surface. For that reason, scientists will continue conducting repeated surveys of Biscuit Basin in the coming months. Comparing aerial imagery, thermal observations, detailed ground mapping, and satellite measurements allows researchers to determine whether the expanding crack has stabilized or remains active. Monitoring also helps identify additional changes that may not be immediately visible, including subtle surface deformation or the formation of new hydrothermal features hidden beneath vegetation or mineral deposits. Despite the attention surrounding the expanding crack and newly formed vents, the overall condition of Yellowstone's volcanic system remains unchanged. Earthquake activity continues within expected background levels, ground deformation has not indicated rapid magma intrusion, and volcanic gas emissions have shown no evidence of a significant shift in the deeper magmatic system. Those observations remain consistent with Yellowstone Volcano Observatory's decision to keep the volcanic alert level at normal and the aviation color code at green. That distinction is essential because Yellowstone is both an active volcanic system and an extraordinarily active hydrothermal environment. The heat driving the geysers, hot springs, mud pots, and fumaroles originates from magma several miles and several kilometers beneath the surface, yet most changes observed at Biscuit Basin are occurring within the much shallower hydrothermal plumbing system rather than inside the magma reservoir itself. The latest developments therefore reinforce an important scientific conclusion. Yellowstone is indeed changing, just as it always has, but the available evidence indicates those changes are currently confined to the park's dynamic hydrothermal system. The expanding crack, the newly formed boiling pool, additional steam vents, and intermittent hot water spouting all reflect an underground plumbing network still adjusting after a powerful hydrothermal explosion. They serve as another reminder that Yellowstone remains one of the most geologically active places on Earth, where the landscape continues to evolve even while the volcano itself remains at its normal state of activity.